really pleased to have a fantastic group and panel on today to talk about a burning issue that faces both our industry and society. And the topic is, of course, it's about climate change. The drivers, I think, for what we're trying to do here are ones that are pretty well known, but perhaps are worth stating here briefly. So firstly, we are seeing the need from the management and executive teams of the insurance industry who are demanding the ability to be able to model and understand climate risk throughout their businesses. And I think that's a fairly obvious requirement that we probably all would appreciate. But I think that's supplemented in those demands by two other sources. So one of them is a regulatory driver. And we've seen, I think, a considerable amount of thought leadership that's come from regulators around the world, perhaps to some degree led slightly by Mark Carney, his work and the work he's done with Bloomberg as well, actually. So those two have actually provided a huge stimulus to this sort of debate. And I think that the new area that perhaps some people may not be completely aware of is we're seeing the new capital coming, or in fact, existing capital in some cases, coming into the industry, making the assumption that the risk takers in the insurance or reinsurance industry, who by most definitions are leaders in their field, are still struggling to understand the effect of climate on their business and on their solvency capital requirements. And I think that's a surprise to many. So that's really, those things are really driving the demand and the need for enhanced ability to model climate risk in the tools that are well known throughout the insurance industry. And I think what we're going to explore today is four people that have got different perspectives on that. Two explicitly with a very, very heavy and existing science background, and two that have got more of an industry background to try and see if we can understand a little better about what the future holds for our ability to model the changing climate that we need to do better and indeed very, very quickly.
So I work for Lloyd's of London, and part of my role there is to understand and manage our role to natural catastrophes. So thinking about climate change is a really important part of my job. When we talk about the risks of climate change for insurance, we can mean a lot of different things. We can mean physical risk or transition risk, or risks related to assets, or risks related to liabilities. As cat modelers, we do tend to focus on physical risk and to some degree risk to property. However, 2020 has taught us just how important it is to consider clash across multiple lines of business, and also how devastating systemic risk can be. Climate change undoubtedly is a systemic risk. We've got food security, water, issues across the whole planetary system. You could even say it's the most fundamental systemic risk there is. It affects all geographies, all sectors, and all classes. So we need to think bigger than just property. In the insurance industry, and especially in the cat risk community, and here I mean underwriters, actuaries, and modelers, we already spend a lot of time thinking about the losses associated with extreme events, and many of these are weather events. So for us, climate change is a risk multiplier. We expect that it will affect the frequency and severity of the extreme events that we're modeling already, and the size and direction of change will depend on the region and peril. And as we'll hear later, there are different levels of confidence in the impact. Fundamentally, when it comes to building our event catalogues, history is just not a good guide to the future anymore. The risks of the past and the extreme events of the past are not likely to represent the extreme events that we're going to face in the future. There's going to be new risk, and there's going to be increased volatility. This is really important because we'll require solutions from the insurance industry where our role is enabling society to function by sharing risk. To allow risk transfer, this sharing of risk, we need risk quantification. We need to understand how the risks we already underwrite might change, over what timescale, and identify any new risks that we might experience as a result of climate change. Of course, when we tend to talk about this, we often start with the hazard, but the risks we're really interested in are the combination of the hazard with the vulnerability and the exposure, the overall financial risk. And this is where we, as an industry, have experience and expertise combining hazard, vulnerability, and exposure in catastrophe modelling. And this is where tools to understand societal risks can be developed. Tools that combine potential changes in future hazard with projected changes in exposure and their resilience. The thing is, when we start talking about this at an industry level, the discussion can often derail. People start asking, yeah, but what about future changes in mitigation? Or what about the fact that I'm going to be writing a completely different portfolio in the future? It'll reflect the risk landscape that we'll be in. It'll have different limits, different deductibles, different attachment points. This doesn't make sense. What about the changes in resilience that we know that we see after events? There'll be some of those. All of these are valid points, but we need to start somewhere. And we need to start with our current portfolios, understanding that any work we do will be a stress test and subject to significant uncertainties. It's also really important to be clear what the question we're trying to answer is and why, to identify the timescale of interest and to have a model which can be built on projections related to that timescale. And we must make sure that the limitations of the analyses are clear to all stakeholders that are using them. Too often, this sloppy thinking. I've often seen this graph of time series. It can be global or regional losses, where the uptick in recent losses is presented as evidence of the impact of climate change. And in these cases, there's only the slightest mention of exposure changes or hardly sometimes any mention of the interaction of natural variability with climate change. The sad fact is that by the time we can see this trend materialize in our extreme losses for definite, it will most probably be too late. So we need to find a way to account for this nuance and complexity, but simplify it in a way that can be communicated without resorting to tabloid thinking. Each of the tools we have has got limitations. Scenarios are really great at getting the message across, but they're pretty limited for risk transfer without any reference to probability. Hazard maps can be great, and you could use them to show the need for different risk selection strategies in a warmer world, but they won't tell you anything about the accumulations you'll face then. Only catastrophe models will be able to provide the full range of outputs that we need as cat risk management professionals. They're the only tools that we can use to interrogate impacts both on an expected basis and tail losses, and the only tools that we can look at to try and understand the potential impacts of different portfolio management strategies for our specific exposures. Of course, the results won't be correct, and they'll only illustrate one, or at best a few, potential possible future outcomes. But they will help us to start to think about potential future strategies. We'll probably face challenges validating these models. And of course, we're going to need to validate them to use them. For all of the reasons we've discussed, historical data just isn't going to help us here. And we'll need to have some kind of climate data sets that we can use to help us do this. As we move on, regulatory interest is only going to increase. Dickie mentioned Mark Carney earlier in his intro and the insurance stress test, which featured scenarios relating to climate change. One observation coming out of this was that we need more and better tools that reflect climate change. And at Lloyd's, we're going to be doing a review in 2021 to look at how syndicates ensure that the models that they use now are adequately representing current climate, so including the climate change which has happened already. As an industry, we need to engage with the scientific community to find ways of ensuring that the latest research is incorporated and that we're aware of all the assumptions that we're making and that underlie our modelling so that we can communicate these successfully. We'll hear about ensembles later from Julia. Climate cat models are crying out for something like ensembles in communicating the outcome. Oasis already has wheat sheaf capability, and I really think that this kind of functionality will be even more important in understanding climate conditioned outcomes. So I've outlined why I believe CAP models for climate are a necessary tool and 5 challenges. These are the need to understand climate change as it affects both current and future extreme events, the need to have projections relating to commercial timescales, the need for new data sets to validate future models, ongoing and increasing regulatory expectations, and finally and critically, being able to communicate the uncertainty and being really clear on the limitations of any analyses that we present. I think that it's obvious that there are no easy answers and no one group of people has them. But there's an opportunity for the CAP modelling community to play a critical role in risk quantification, which will benefit not just our industry, but the whole of wider society. I really believe that the only way that we're going to succeed is that if we work together across the insurance industry, across disciplines, and with the academic and scientific community to access more data and develop better tools. These partnerships are really the only way we're going to understand the changing risk of extreme events in a warmer world.
I've got actually 6 points that I've got on screen in front of me, if you see my eyes flashing up and down occasionally, that I wanted to expand upon in the 5 or 10 minutes that I've got. The first one is just the idea that when it comes to climate risk, it's an issue that we're often referred to as it being something that's out there in 2040, 2050, 2100. And for me, it's an issue that's a present issue. I saw a fairly senior figure in our industry recently mention that we have these great things called catastrophe models, and they're doing a great job at working out our present day risk, and we should be using them to work out the future risk. And I completely agree with the second half of that statement. I certainly don't agree with the fact that the catastrophe models that we have nowadays are adequately giving us a view of the present day risk vis-a-vis the amount of climate impact that there is on present day risk. And I certainly think that something that will make boards sit up a little bit more is if they're led to understand that potentially the CAP models that we're using for working out our yearly insurance contracts potentially don't have factored in elements of climate risk about them in today's money, let alone what we might see in 30 years' time. And I think that's a really big 2-step process, working out the risk through climate now and then looking at it in the future. The second point I wanted to mention is just the interface between climate and catastrophe risk. Through work with the regulators, we're often required to work out what our 200-year risk is. And if you wanted to work out what the sort of risk of the events that happen once every 200 years, you need a lot of data. So it's a difficult proposition whereby we're trying to work out what our 1 in 200-year risk is using climate models. And from looking at the research and looking at what's going on in academia, I see pretty much all of the heavy lifting in terms of the really large climate model runs that will enable us to try and understand what happens every 200 years, for example, is happening in academia and has been happening in academia for several years now. I don't see as much of that, the ability to hold the amounts of data that we see in the vendor modeling companies, for example. I'm not pointing a finger here in particular. Some data I was looking at recently for global climate that looks at 100 simulations from 1951 to 2011 and looks at that into the future. It's got up to 2 petabytes of data. That's an enormous amount of storage that's required. And a lot of this heavy lifting is solely being done in academia. So that's where I believe most of our answers should be coming from. The third point, which is linked to the idea around catastrophe risk, is just the fact that we are looking at high intensity hazard gradients typically, and they require pretty high resolution of climate models. Some hazards, for example, European windstorm, we're getting to a climate model resolution where we're able to resolve the risk and the size of the footprints in the models. In US hurricane, where typically maybe Cat 4, Cat 3, Cat 4, Cat 5, really small intense storms typically drive the EP curves in Cat modeling, is where we're maybe falling down with the climate modeling situation. But, and this is where I refer to Adam and his co-workers, they've been thinking for several years now. I believe Adam's paper, most recent paper looking at climate model methods for adapting climate models to be able to simulate hurricane hazard more realistically, has been out for 3 or 4 years now. So Adam, for example, and his co-workers have been thinking about ways of bypassing areas of climate model weakness to be able to still use the models to create useful climate-focused catastrophe models. And again, going back to the point that a lot of the thinking is going on in academia around this topic. The other thing for me is when it comes down to looking at the climate delta, how much risk is going to change into the future. A lot of work has been done on the hazard side of things. I certainly don't believe that we necessarily need really complex vulnerability and exposure components to understand the delta of how much the losses are going to change. To give a very simple example, I was looking at 6,000 years of European windstorm data. I used a very, very simple cube of the wind speed above a certain threshold, some fairly realistic exposure across Europe, and I was able to mimic typical results that you got from vendor models using very, very straightforward, simple exposure and vulnerability. And I believe to be able to get straightforward initial results out of climate models, we can use some very, very straightforward exposure and vulnerability data. Fifth point I want to mention about is obviously a lot of academia thinks about hazard, and we in the insurance industry often will want to be thinking about exposure and vulnerability as well. And we've got to think about when we're moving into the future, how exposure might be changing, also how building stock and the vulnerability curves might be changing in response to changes that will happen in the future of hazard. And simple things like what size of vulnerability adjustments might help to counteract the future changes in hazard. Again, using these very, very simple, straightforward models, we can maybe start to get answers about surrounding this. Where can exposure grow without necessarily big changes in the losses that may come around through climate changes in the climate hazard? Or which areas, for example, are we seeing where exposure growth potentially is simply swamping the changes that we're seeing in climate hazard? So again, using these simple models and simple exposure, simple vulnerability tacked onto the really quite detailed hazard, we can start to answer some questions, I believe. And the last thing I wanted to make that is more of a byproduct of these enormous data sets that are being run is, again, the one thing that I think that is great that it comes out of academia is that they are effectively global models. They are enormous data sets that are being run across the whole of the globe. And the first thing for me that jumps out straight away is that there's a great potential here to look at the correlation between basins, Australia cyclone, Europe windstorm, Japan typhoon, etc., etc., etc. Correlation between perils and regions, not just now, but into the future, and whether these are an impact that is going to come around through climate change. So I've jumped around quite a bit there, but these are the things that always seem to jump to mind when I think about the interface between climate modelling and cat risk.
Richard, thank you. Great way to set the scene. I think that's fantastic. So does anybody feel like they want to make a comment or a question or a point to Richard's statement before we move on to the next one?
I think you're right, Richard, that the scale of the enterprise today to really utilise all the climate simulations and predictions is beyond the scope of many of the vendor companies to embrace. I would say I think it's not just academia that's driving this. I have to say the really big operational centres are also driving this, and I'm going to talk about the Met Office capabilities later on. But what's clear here is that what we really need is partnership. What's been so successful in the UK is that academia and the Met Office, the Hadley Centre, have partnered up so that they can work together on the same data with the same models on the same compute platform. And that's incredibly powerful. And I think it's a model that we need to think about going forward with the industry as well, is whether we could do better in partnership so that we can really exploit the enormous wealth of information that's around now in these huge data sets from simulation and prediction. To me, that's a big win that's sitting out there.
Brilliant. Adam, anything you want to say, or just happy to carry on?
I think I'm going to address a lot of the same points Richard made, so I don't have a comment exactly, but
that's fine.
I mean, we're in agreement about almost everything. So,
okay. Well, look, so Adam, let's go you next, and then Julia can follow up, and then we can see if there's any other comments and questions.
So what we're talking about here is calculating the risk from disasters. And when we experts get to talking about the details of that, it seems very technical, but the answers have real human implications. They affect reinsurance contracts, obviously. That seems pretty abstract to most people. But more and more, as companies are doing climate-related financial disclosure, these risks estimates are going to affect the flow of private capital through the global markets more broadly. And they also affect international aid for disaster risk reduction and climate adaptation and poverty mitigation. And these things affect the lives of large numbers of people, including some of the most marginalized. So as populations increase and land keeps being developed, including very hazard-prone areas, and the climate changes, the impacts of the estimates of disaster risk that we come up with are going to be more and more consequential for more and more people. So it matters how we do this work. And in the past and up to the present, the reinsurance industries relied primarily on proprietary models designed specifically for the industry's purpose. So these have been largely empirical, bootstrapping the historical record in one way or another, and they haven't incorporated climate change yet in a serious way, as Richard said, certainly not in a way that takes on board the full scope of what's available in the climate science community, in academia and government. The traditional CAP models have also been region-specific and focused naturally on the regions where there's the most insurance penetration. So all of this made sense in the historical context that the models grew out of, but it's not enough to meet the present or the future need. So because our estimates of disaster risk are so consequential in this rapidly changing world, they have not just business implications, but real human ones, ethical and social and political. It's essential that they be subject to robust, open, and global scientific debate. And that can't happen if the models are all proprietary. The benefits of openness are plain, I think, if you look at the climate science community, leaving aside the science for a moment itself, but just the model of how we've been doing business, where the coupled model intercomparison projects that are associated with the IPCC since 2007 have put all the data produced by all the world's climate models that are involved on public archives. So the output from all the world's major climate models can be analyzed together as a group by a scientist anywhere. And that has revolutionized the field, especially because it allowed everyone to understand the uncertainties better by looking at the whole multi-model ensemble, the spectrums of different models that give different answers. And most of the model codes themselves are also open source, by the way. But of course, climate science is not just relevant in the model of openness, but also in the science itself. I think everyone understands now that any estimates of climate-related perils, tropical cyclones, floods, droughts, wildfires, severe convective storms, have to address climate change in order to be relevant today. It's not just a problem, as Richard said, for the future. The climate has already changed significantly, and we have to reckon with that. The philosophy that says we don't need to use predictive climate science because reinsurance contracts are written year by year and we'll just price climate change in as it happens, I think it's now become broadly understood that that is not defensible, because we're talking about rare events that do most of the damage. So recent observations aren't enough. That's why we have CAP models, right? Because the history is not long enough, so we need huge synthetic event sets to capture the risk accurately. That's the same reason, though, that the historical observations don't capture climate change, because you need very, very long records to see the signals, and the climate is changing faster than that. And even whatever climate change signals are in the observations, to understand those, you have to separate natural variability from the anthropogenic signals if you want to understand what's going on and quantify it right. Because there is already a climate change signal in what's happening today, and we need predictive climate science, not just historical observations, predictive science, including climate models, to see it. Now, that doesn't mean that climate change has yet had a huge impact on all the perils of interest. With some of them, like wildfires, I think we're already seeing a global warming signal pretty clearly. With others, maybe there hasn't been much change yet, or maybe we can't tell from the observations within the uncertainties, which are very large in many of these types of events. And we can be sure that there's no one model that's going to deliver the answer that's true and precise. But these results are so important that we should be using all the science we have to assess the climate change signal, and as well as the answer overall. And that requires a broader, deeper, and more active engagement with the field of climate science as it exists largely in academia and government than the insurance industry has traditionally had. Now, how to do it technically? Well, in principle, dynamical models are the right way. These are the models that use the law of physics as explicitly and as precisely as they can within the limits of computing power. And these are the models that have been used for many years for weather prediction and for understanding and predicting climate change itself. In principle, these kinds of models can simulate the climate and the extreme weather events that cause the disasters together in the organically connected way that they really are in the atmosphere. We're trying to understand natural catastrophe risk. These kind of models are ultimately the right tools. And for some perils and some circumstances, they're already getting to the point where they're usable for this purpose. But the dynamical models have their limitations too. They take a lot of computer power. So they're very expensive to run. They produce enormous quantities of data that's burdensome to analyze. And to simulate the extreme weather events that really matter the most for disasters, they need to be run at the highest resolutions available, which makes those problems, makes them even more expensive. And in general, they still have biases as well. It's not clear that they're always getting exactly the right answer. So at this moment in history, I think we do still need traditional catastrophe models or something closer to them that incorporates more predictive climate science. So in our group, inspired originally by the work of Kerry Emanuel at MIT starting in the early 2000s, we've developed a hybrid statistical dynamical model that combines empiricism and predictive climate science. Richard described it briefly. It allows us to take climate model output that predicts climate change, but that doesn't itself predict the tropical cyclones very well. But then we downscale it with this statistical dynamical model to produce our own synthetic tropical cyclones that we can plausibly argue are consistent with the climate produced by the climate model, and do that globally. So that's one approach. We could debate whether it's the best one or not. I don't think that is the most important debate. I think what's important is that we have a diverse spectrum of models built using scientifically defensible methods, and our understanding of the scientific uncertainty in natural catastrophe risk should be based on that spectrum of answers that the models get. And then we can argue about whether every model is equally good or some are better or others outside the pale or what have you, just as we do in the climate science space. So I think to do this, we should have greater engagement, as Julia just said, between the academic community, scientists, government agencies, as much as possible, and the private sector, of course. And I think the resources can and should come from both industry and government. And this requires evolution, not just from the reinsurance industry and the catastrophe modeling community, but also from climate science as well. In our field, climate science that is, we know a lot about extreme events and how they're related to climate, but a lot of that knowledge is not directly relevant to the practical problem of risk assessment. So I think we need to draw in more of my colleagues, and we all need to think together about problems like how to draw the right balance between calibration and bias correction, which we have to do to get the answers right enough compared to history on the one hand, but also genuine predictive science, which we need to capture how the present and future are different from the past, but which of course can give us the wrong answer. So that's a compromise we all have to think through. We have to think hard about what's natural variability climate change and in what ways and how much that matters for the practical problems we're trying to do. And we definitely need to think together, as Richard referred to a bit, about how to quantify exposure and vulnerability globally using public data. Maybe we can get away with something very simple, but how simple and in what ways and what data it's based on is something we have to think through. So if we do all that, we'll have more robust, scientifically defensible and valid estimates of climate risk and natural catastrophe risk. That doesn't guarantee that all the decisions made with those estimates will be right in all possible ways, but I think it increases the chances, and it's the right way to do it.
Fantastic, Adam, fantastic. Thank you, brilliant. Anything pertinent that people want to refer to now or ask a question or make a comment or something?
My only additional point is something that I wish I'd said that Adam had mentioned, is this whole around the whole topic of calibration and how we are, I think, a bit too wedded to history as a way of justifying that a model is good. And rerunning history multiple times will show you this, that your last 120 years of hurricane landfalls and the losses that come from those can be pretty variable. So it's a great conduit to reopen this debate, actually.
Fantastic. So I think we can probably just say, Julia, we can hand over to you. So Julia, perhaps you'd just like to give your thoughts.
Well, I just want to start by saying, of course, we're here because we're taking the planet into uncharted territory in many, many respects. And we're moving actually already today from what we would regard as the familiar towards the unusual relative to our lived experience. And that's going to challenge how we think about extreme events and how we think about the risks we face. And so I've got three questions that I want to address. First of all is, well, how well do we know today's physical climate baseline risk from extreme weather and climate hazards, due both to the natural variability of our climate system, but and indeed from ongoing climate change? And we've already heard other speakers touch on this point. The observational record is far too short to characterize the nature of extreme events, even for a climate without global warming. And then the second, I think, really important question now is, how will our physical climate risk baseline evolve as the world warms in terms of changes in the frequency and/or intensity of hazards? And that's moving us very much away from thinking about climate change in terms of global mean surface temperature to thinking about climate change and what it means for you and me, where we live and how we live. And finally, I think there's a big challenge really on how we should assess risk in very complex situations. Because if you look at virtually every catastrophe that the insurance reinsurance industry considers, they involve complex combinations of systems and situations. And that can be quite paralyzing to make progress, and paralyzing in how we can bring the best climate science into the discussions. So the first thing I wanted to say was that we've been, I think in the last decade, probably, going through what is often called the quiet revolution in simulation and prediction, which may have sort of bypassed a lot of the industry. But there have been absolutely amazing changes in our ability to simulate and predict weather and climate. And the first is, of course, the resolution and complexity of our global models. We're no longer running them at 100-kilometre granularity or more. We're typically, certainly in forecasting down at 10-kilometre granularity, and now often in climate prediction around just a few tens of kilometres. And what that has meant is that they are much more successful at representing what we call the synoptic drivers of extreme events, the frontal systems, the storms, the anticyclones, all those things, blocking situations. They're captured much more accurately in these models. And then, of course, we've had the emergence now of these kilometre scale regional models, which have actually revolutionized weather forecasting at the local level. And they are now routinely run, ensembles of these routinely run operationally at 1 kilometre, with lead times of as and indeed a climate timescale for years. And what they give us is an unprecedented view of how the local meteorology is evolving. And they're telling us things that we just didn't know a few years ago. And we can take the output of these models at the kilometre scale with much more confidence then into impact models such as flood models, and really talk about impact scenarios and narratives. So that's the quiet revolution that's been going on. And what it's allowed us to do is quite a few things, which I'll now just cover off. The first thing is that we've been able to use these new generation of high resolution climate models to estimate risks from extremes. So these are worlds that might have been. So we're talking here about Ed Lorenz and his saying, one flap of a seagull's wings may forever change the course of the weather. Of course, we think about that in terms of ensemble weather and climate prediction. But actually what it also tells us is something that Richard's already touched on, which is that there are many paths that the world's weather could have taken in the past 100 years. And what we've observed is just one plausible pathway. So there are a myriad of possible pathways that the world's weather could have taken in the last 100 years that would have been perfectly plausible and would have given us completely different set of statistics about extreme events and other aspects of our climate system. So the question that we came up with a few years ago is, can we use these multiple realizations of our weather from simulations to find unprecedented extremes even for the current climate? So can we use them to tell us about our baseline risk? And the answer is that yes, you can. And we use this in ANGA as part of the UK's National Flood Resilience Review. We've had some very serious flooding for several winters in a row, and the government was naturally concerned that the extreme flood outline maps weren't fit for purpose. And what we found was that if we used a very large ensemble of climate simulations at reasonably high resolution, so they were capturing the weather regimes that drive extreme rainfall events in the UK, we were able to find that actually there were a large number of extreme events that lay outside the observational record going back over the last few decades. We called them black swan events, and the size of the event set was nearly 2 orders of magnitude larger than the observational set. And what that allowed us to do was to estimate with quite a lot of confidence statistically what a 1 in 100 year or 1% risk of exceeding the observed monthly maximum rainfall could be for any winter in particular regions of the UK. And what we found was that on average, indeed in any winter, there's a 5 to 10% risk that you'll get an unprecedented rainfall maximum. And that actually there's a 1% risk in any winter of exceeding that observed maximum by 20 to 30%. Now that's quite a lot. And that's just from natural variability. This is not adding on what is already happening to heavy rainfall from climate change. Now, when you take that number and stress test an environment with that number, and we did a set of cases for the review, and the one I'm going to talk about here is looking at a major flood in my hometown, Exeter, where the Met Office sits in 1960. And we remodeled that using the kilometre scale model. And then we did a stress test where we added 30% more rain than actually fell in that event in 1960. And then we took that through to look at the flood inundation maps for Exeter. And what it showed was that actually, even with present day alleviations in place, several thousand more homes would be flooded if that event had 30% more rainfall. So we're in quite a lot of trouble, even from natural variability, that we don't understand our baseline risk. And so these event sets, synthetic event sets, are incredibly powerful ways of really actually improving our understanding of our baseline risk. I think they're almost essential. And then, of course, the other big change that I've already talked about is that we've got these kilometre scale regional models now, which allow us to do this downscaling, which is akin to what Adam was talking about his statistical dynamical methods. But we can actually do that now too with dynamical methods using kilometre or even sub-kilometre models. And these models actually are giving us really new insights now into the climate risks we're facing, say, in the UK. And we know, for example, when we look at climate projections run at the kilometre scale, that our risks may be substantially larger from floods, storm surges and wind damage, just because these models give you so much more local information. And they also involve the dynamics of particularly convective storms. And so you get this really big enhancement of the intensity of convective storms as the world warms. So these are really exciting new developments that I think we should be bringing in to the way that we assess the probability of hazards and effectively the tails of the distribution. And then finally, I think the other big thing that's really come up is the way that we can now use weather regimes as proxies for high impact weather at the more local scale. And this is now being used extensively in extended range forecasting and indeed in climate prediction. And the really great thing about weather regimes is that you can also look at clustering statistics. You can look at antecedent conditions before a flooding event, all those sorts of things, which are quite difficult to do otherwise. So I think the use of weather regimes is something that, again, we've touched on so far with Adam and Richard in particular, that there are large-scale proxies that can help us a lot, which give us a sense of what we might be facing in terms of frequency of risks. And then finally, I think we need to think about how we communicate or think about risk more generally, and think about not just using probability space, which is actually for some people quite difficult. And one of the other complementary ways you can think about climate risk, particularly in a complex situation, is to use storylines. And the really nice thing about storylines is to actually take a particular, either a real event or a synthetic event from the future, for example, and ask what were the relevant causal factors that led to that event. How might climate change have contributed to those causal factors? And how might future climate change make a future such event even more impactful? And the nice thing about storylines is that you can follow in detail the sequence from the natural variability or some aspect of the weather or climate regime through to the local impact of, say, extreme rainfall or flooding. You can then look at the properties at risk, and you can ask questions about where the biggest uncertainties lie in my assessment of that storyline. And there are some very nice examples now of using that, not just to look at flooding, but also to look at wildfire, which in itself is a complex problem involving many players that come in to actually to elevate the fire risk. So I'm giving a couple of examples, and I think we need to think how we can bring the storyline approach into the more traditional ways of using probabilities and looking at tails of distributions as a way of stress testing our resilience and stress testing whether we actually really have captured the full breadth of the risks that we face going forward.
Fantastic, Julia. Thank you so much. So any comments, observations on anything that Julia said?
Yeah, first of all, thanks for your wonderful remarks. I have two things. First, thank you for bringing up the storylines. I think this is a really important point. It's a way of thinking that I think to some extent the reinsurance industry already uses a bit. I mean, not so much in actual risk assessment, but in the sense that people do kind of come up with imaginary events and in what those would have looked like as a sort of stress test. And if you think, without assigning necessarily probabilities to it, that's what makes storylines different than the probabilistic methods, as you said. And if you think about how the financial industry does stress tests, it's if this happened, what would happen to your balance sheet in your business, and you don't necessarily have a probability. Obviously, somebody thinks the probability is not zero. In areas where certainty in climate predictions are large enough that we can't be sure, we know that there probably is a climate change signal, the storylines are very valuable because they kind of let people connect to what possibilities are, how we'd react to things that, although maybe outside historical experience, are definitely not outside the realm of possibilities. But I think you're absolutely right about that. I'm so glad you brought it up. Then I wanted to ask a question. So you described these just amazing things that Met Office has been able to do with dynamical models. Excuse me, and some other centers around the world have as well, and it's true. I mean, the capabilities of these models have advanced so much; it's just astonishing what some of these results, how vivid and detailed and accurate the results of the model. But I just wanted to ask you to sort of comment a little more on the sort of degree of fitness for purpose to the disaster risk assessment business as done in reinsurance. Similarly, so where people have large categories, catalogs of synthetic events of different kinds, including some like tropical cyclones and maybe severe convective storms, where they're still at the margins of what the models can do at the full range of extremes. And people are sort of, the reason people use statistical models is because they aren't limited by resolution. I mean, they do capture the most extreme events by construction. And so given, how ready are the dynamical models to sort of produce exactly what is needed for these applications? I mean, large catalogs of extreme events that people can access easily and sort of work with for all the different perils. I mean, where are we in that space, and which should be handled directly by global models, by regional models, by downscaling with other means? Where are we in that spectrum?
You're right. I mean, we've had this amazing transformation actually of capability, largely through compute power. But I think, it's fair to say we're at the start of a journey here of how we really use these simulation as synthetic event sets. I think going forward, they'll become more and more prominent. But I think the fact of the matter is now that they are good for things that I would call synoptic scale type events like windstorms. I think we can have a really good go at windstorms from a global model with a resolution of 25, 50 kilometers. I think large-scale flooding we can probably have a go at using the sort of techniques that I described in just now. But I think when we're getting down to more local systems like extreme thunderstorms or even like tropical cyclones, we're not there yet. I think we can use things like the tracks of tropical cyclones from high resolution global models to say about the changing risk of landfalling tropical cyclones, for example. But we certainly can't say anything about their footprint on an area when they have a landfalling hurricane. And that's where I think we still have to have, this hybrid approach. I mean, I think that is absolutely the way forward for now. The other thing is that we need to be able to get that capability to use the kilometre and sub-kilometre simulations, in a sense, almost on demand in any location of interest. And actually, that requires some actually technical changes and probably a lot more compute power to do that. But I think ultimately, that is the way we should be going. And so I think we could accelerate all of this, particularly in terms of the insurance industry, by better partnership, because actually that's the way in which opportunities, and we can, do some trial test beds. We can learn together on what's the best way to bring all these different capabilities that we have in our science community to bear on improving risk assessments going forward, not just for the insurance industry. I would say this is a sort of a universal need, actually, of anybody that has to manage risk to infrastructure, to lives and livelihoods. I mean, I think we must do this and with pace.
Good thoughts. Adam, do you want to follow up here?
No, thank you. Those are wonderful answers.
Richard, anything from you?
Oh, I just mirror what Adam was saying about just the storyline topic. in the sense that we have these in insurance in the form of realistic disaster scenarios in a way. But I've been doing a bit of work with Lloyds recently just to talk about, you have a realistic disaster scenario as your sort of moment in time, as it were. This is what could happen. But it's also, as I've been talking with Lloyds about this, is trying to talk about how might this disaster scenario change how might it move along a loss curve when you look at the impact of climate change. So is your realistic disaster scenario that's your 110-year event, are you happy with the fact that this could become a 1 in 60 or a 1 in 50? It's a lovely way of talking about things.
So I just want to say thank you to our speakers today, because I think that if you look at the conundrum that we're facing right now in society and in insurance about understanding risk, I think our speakers today have really set out a roadmap and some set of requirements that we need to fulfill. Need being the operative word to make sure we can do this. And I'm really pleased that when I set up Oasis 8 years ago, one of the functions that we wanted to be able to do was act as a much more efficient translation function. As already been said, to have a conversation about climate and to have a conversation about risk. And I think that by the end of this year, we'll have more climate condition count models available on the Oasis platform than anybody else in the world, as defined by this CAT modeling paradigm. And that's just proof that this conversation is going to continue. And today's video really is just a start of that. So thank you to you all. And please, those watching, use this as a starting point for your conversation to exploring how we can model and understand climate risk better. So thank you all.